All right, we continue to work on solving a system of linear equations using the elimination method. In the previous two videos, we were able to eliminate one of the variables just by adding or subtracting the two equations that were lined up in standard form. In this stage of elimination, we will find that sometimes neither adding nor subtracting will eliminate either of the variables. Looking at this initial system that they give us for the example, if I tried to add these two together, I'd get 7x plus 9y equals negative 13. And neither of my variables will eliminate. Well, you can always try subtraction. If I tried to subtract this system, 5x minus 2x is 3x, 6y minus 3y is 3y, and negative 8 minus negative 5 is negative 3. Subtraction did not eliminate either the x's or the y's. Addition did not eliminate neither the x's nor the y's. This is happening because we do not have opposite terms on either variable. We see that the coefficients on our variables, if you can see this, 2 and 5, are not opposite of one another. The coefficients on the y, 6 and 3, are not opposites of one another, so I can't get them to cancel out with addition, and I can't subtract them to make them zero out either. This example that's written in for you in your notes takes you through the steps that you might take in order to still go ahead and eliminate one of the variables, and it emphasizes the start at step 1. Step 1 in the elimination process is to multiply one or both of the equations by a number to create opposites. And I don't have the concept summary for elimination here, but it's in your notes on a previous page. But step 1 is going to ask you to multiply either one or both of the equations by a number that would create opposite terms. And I'm going to show you what that means in this example. Check your progress 1A. In this example, a system of linear equations, if we try to add the two equations, we'd get 9x minus 5y, when I add them I get negative 9y equals negative 9. And none of the variables cancel out. If I tried to subtract them, if I just try to subtract the two equations, I'd get 3x plus 5y equals 29. And again, I still have an x and a y, so neither of the variables are canceling out with addition or subtraction. Again, that's happening because we don't have opposite coefficients on the x's or on the y's. We could make this happen legally if we can multiply one or both of the equations by a number that would give us opposite coefficients on either the x's or the y's. Typically, you'd have to make a decision ahead of time. Do you want to eliminate the x's or the y's? And you could do either one. Doesn't really make any difference. But one of them hopefully stands out as an easy one to eliminate, and that is that's x's with coefficients of 6 and 3. 6 and 3 are not opposite of one another, but if I were to multiply through that bottom equation by 2, then the coefficients on x would be the same, and I could cancel them out using subtraction. So over here I'm going to rewrite what the bottom equation looks like when I multiply through by 2. I get 6x minus 14y is equal to negative 38. I'm just going to sort of copy that top equation over the top of it. That's 6x minus 2y equals 10. Now, I've created through multiplication opposite, or I should say the same coefficients here on x. If they were opposites, I could add to cancel, but they are the same, so I'm going to have to subtract the two equations to make them eliminate the x's. When you subtract the two, 6x minus 6x is 0x. Negative 2y minus negative 14 is positive 12y. 10 minus negative 38 is like 10 plus 38, and it gives you 48. By making those coefficients on x the same and then subtracting, I have eliminated the x term, giving me just 12y equals 48. A real simple solve, dividing by 12, we get that y equals 4. Now you're looking for the point xy where the two lines intersect. So far we know that y is 4, and I'm looking for the x coordinate. I'm going to take the 4 that y is equal to and substitute back up into the very first original equation. Try to sort of stick with the process, the same as the last couple of times we've done this. And solve for the missing variable x. We get minus 8 equals 10. And we get 6x equals, adding the 8 over 18, dividing by 6, x equals 3. The alleged point of intersection at 3, 4. And a check would show that that point actually does work in both equations. Here I've just found it in the top equation. I have to go back to the first original equation, not the one I made or created, but this very first original equation. The second original equation was 3 times x minus 7 times y is equal to negative 19. That's 9 minus 28 is equal to negative 19. 9 minus 28 is negative 19, and that equals negative 19. Solving a system of linear equations when the variables do not have opposite coefficients can be done as long as you can multiply one or both of the equations by a number that would make them the same. In example 1b, we're lined up vertically, but our coefficients are not opposite of one another. 9r and 3r, and that would be a 1q and a 2q. At this point, we have a choice to either eliminate the r's or eliminate the q's. If I wanted to eliminate the r's, I would have to multiply the bottom equation by 3 so that I get 9r on the bottom, and then I simply subtract the two equations. If I really wanted to eliminate the q's, I could just multiply the top equation by 2. Multiplying the top equation by 2 would give me 2q, and the q's would cancel out, again with subtraction. The choice is yours. It doesn't make any difference which way you do it. You just want to multiply by as small a numbers and as little as possible, or as little change as possible. So since I already have it up there, I'm going to multiply the top equation by 2. That gives me 18r plus 2q is equal to 26. I'm not going to change the bottom equation, but I'm just going to move it over so that it's underneath the first one. And having them lined up, you can see that the q's will eliminate. I can eliminate those q's if I subtract, because they are of the same sign. So I'm going to be subtracting the two equations. 18r minus 3r is 15r, and 26 minus 4, that's a problem. 26 minus negative 4 is what I'm doing here. Sorry about that. 26, I got to subtract a negative 4, and that's really like 26 plus 4, which is 30. Dividing both sides by 15, I get that r equals 2. Now, searching for that second variable, if r equals 2, I need to know what q is. So I'm going to take the r equals 2 and substitute it back into the first original equation. And you get that 9 times 2 plus q equals 13. 18 plus q equals 13, and q equals negative 5. The alleged point of intersection is 2, negative 5. And now we just need to check that. Our check would be putting the point into the second original equation, that's 3 times 2 plus 2 times q equals -4. That's 6 plus -10 equals -4, and it works.